Hi, everyone. Thank you for joining my presentation. I'm Mahshid Ghanbari, a PhD student at Colorado State University, and today I'm going to present our study about modeling compound fluvial and coastal flooding under sea level rise level. So flooding has caused significant losses to people and property across the world during the course of last decades, and climate change is putting greater pressure on cities by increasing the frequency and intensity of flood events. Extreme coastal events such as storm surge caused by Hurricane Harvey is happening more during recent years, and minor coastal events, or in other words, tidal or nuisance flooding, are happening with more frequency and have become a serious challenge in coastal cities. More extreme precipitation events have also increased the frequency of both pluvial and fluvial events. The pressure on coastal cities are higher because they are exposed to different types of flooding, such as tidal flooding, storm surge, and riverine flooding. If these events occur simultaneously or in close succession, the impact of flooding may increase. If we ignore this coastal riverine flood interaction, we may underestimate the flood risk. An example of recent compound flooding is the co-occurrence of heavy precipitation and storm surge from Hurricane Harvey, which caused huge flooding along the Gulf Coast of Texas. So in regions where total flood level is influenced by both extreme seawater level and extreme river discharge, considering the simultaneous occurrence of these two flood drivers is important to estimate future flood risk. The previous studies show that the number of these compound events has increased over the past century at many of coastal cities, and we can associate this to the climate change. So it is important to examine the compound risk from coastal and riverine flooding with considering the impact of climate change. Sea level rise is the most significant impact of climate change in coastal areas, and it's an important factor to include when we want to assess the future flood risk. Here you can see the past and projected changes in global mean sea level based on different sea level rise projection scenarios. And the available projections is categorized from low to extreme sea level rise scenarios. In our study, we use regional sea level rise scenarios based on intermediate low and intermediate scenario, which correspond to 0.5 meter and 1 meter global sea level rise. And the reason for this is that these two scenarios are the most probable scenarios by mid-century. Climate change is also influencing extreme hydrological events such as changes in extreme heavy precipitation intensity and frequency, which subsequently may lead to increase in extreme stream flow discharge. These changes have an immediate impact on the risk of riverine flooding. So the main purpose of our study is to assess the compound major coastal riverine flooding risk under climate change, including sea level rise and river flow change along the coastal United States. And to achieve this purpose, we propose a bivariate flood risk framework and applied that to 26 estuary locations along the coastal United States. And here you can see the studied locations, which for each locations, we use the coastal and riverine data. So first, how we categorize compound coastal riverine flood events. Impact flood thresholds are established for many tidal and river stations in the United States by NOAA and USGS for forecasting purpose and also securing public safety. Flood categories based on exceedances over impact flood threshold describe the severity of flood impact. So while minor flooding refers to events with minimal or no property damage, moderate flooding is with some inundation of structure and roads and has relatively considerable damage to private and commercial property. And as flood level increases to major flood threshold, inundated area and infrastructure impact increase significantly. So in this study, we focus on simultaneous or near simultaneous exceedances over major flood thresholds and define that event as compound major coastal riverine event. The data used in this study are categorized as coastal and riverine component data. For coastal component, for each station, we obtain hourly observed seawater level data, major coastal flood thresholds, and regional sea level rise scenarios. And then for the riverine component, again, for each station, we obtain daily river discharge, major riverine flood threshold, and projected stream flow discharge, which is driven by the variable infiltration capacity or simply weak model. Since we are interested in estimation of flooding hazard, we need to apply the bivariate model just to the pairs of high value to prevent representation of extreme values with bias. So we use threshold excess method to identify extreme seawater levels and river discharges. And then we select the pairs when seawater level and river discharges value exceed the threshold within ±1 days to finally have the pairs of extreme seawater level and river discharge. Then the significance of a statistical dependence between the paired data is assessed using Kendall rank correlation coefficient. And then the paired data with significant dependence are fed to a bivariate model. Several parametric and non-parametric methods can be used for bivariate analysis. We decided to use Coppola method since using this method, the marginal distributions can be selected without any limitation. So for random variable X and Y, there is a unique Coppola that describes the dependence structure between the random variables with marginal distribution of Fx and Fy. So we need to know the marginal distribution and also the joint distribution using Coppola. For the marginal distributions, we used generalized Pareto distribution since we use threshold excess method to identify extreme pairs of high seawater level and river discharges. Then the best Coppola is selected among 26 different Coppolas based on the Bayesian information criteria. As I mentioned, our main goal is to incorporate the effect of climate change in the proposed bivariate flood hazard assessment. So either the marginal distribution or the dependence structure between variables or both can be non-stationary. Here we consider the non-stationary effects of climate change in marginal distribution of high seawater level and river discharges. And in order to do this, we used a projected sea level rise scenarios and also projected stream flow discharge. So with that methodology in mind, first we estimate the joint return period of compound major coastal riverine flooding for all studied locations. And here you can see the result for Washington, D.C. as an example. So what we can see here is that if we consider only coastal component, the return period of major coastal flooding, or in other words, exceedances above a major flood threshold is almost 20 years. And then if we consider only riverine component, the return period of major riverine flooding is estimated at almost 50 years. Now, a question is, what is the frequency of compound extremes such as major coastal riverine flooding? Here you can see the joint return period of different pairs of high seawater level and river discharges and as is shown by this red square here, the exceedances above both major coastal and riverine flood thresholds simultaneously or in a close succession appears to be a 120-year extreme compound event. However, as I mentioned earlier, this value is not constant under climate change. So first, we estimated the joint return period of major coastal riverine flooding with consideration of intermediate low and intermediate sea level rise scenario by mid-century. And as can be seen in this figure, there might be a 20% decrease in the joint return period by mid-century under intermediate sea level rise scenarios. Then in addition to intermediate sea level rise scenario, we also consider the river flow change using the projected stream flow discharge. And here, by comparing the green line and the pink dashed line, we can see that although in this location, the frequency of major compound flood events will slightly increase when non-stationarity of a stream flow is also considered, the impact of sea level rise is much greater. And then here you can see the result for the national scale. So the middle panel shows the June return period of compound major flooding under current condition. And the black circles show locations with no significant dependence between high seawater levels and river discharges. So as can be seen under current condition, Northeast Atlantic coast and West Gulf Coast regions are experiencing the highest compound major flood probability. However, future sea level rise scenarios, as shown by panels A and B, show emerging high compound major flooding probability along the Southeast Atlantic coast. So under intermediate sea level rise scenario, by 2050, the Southeast Atlantic coast will experience the frequency amplification of up to 5 times, and all the locations tend to be exposed to major coastal river flooding with return period of 200 to 400 years. For the Pacific coast, despite the significant dependence between high seawater level and river discharge, joint return period of compound major flooding is infinite in most of the locations. And the reason for this is that the major coastal flood threshold has not yet been exceeded in these locations. While sea level rise exacerbates major compound flooding in all locations, the impact of river flow change is especially diverse. As can be seen by panels C, the impact of river flow change is found to be negligible in most of the locations except Southeast Atlantic coast. However, its impact is considerably less than that of sea level rise. And then in the final step, we estimate the risk of failure due to compound major flooding over a 30-year design lifetime from 2020 to 2050. And we define risk of failure as the probability of observing at least one compound major flooding in a given design life. And here you can see the risk of failure on mid-century for major coastal cities with dependence structure between high seawater levels and river discharges. The blue bar shows the case if we don't consider sea level rise. And then the yellow and red bars are shown the risk of failure under intermediate low and intermediate sea level rise scenario. As can be seen under future sea level rise scenarios, the risk of failure due to compound major flooding will increase. However, the changes in risk of failure are regionally different. The highest increase in risk of failure is found for the locations along the Southeast Atlantic coast. The coastal cities along this region are expected to be exposed to double risk of compound major flooding by mid-century. So here is the highlights of our study. So we show that the Northeast Atlantic and West Gulf Coast region are experiencing the highest major coastal riverine probability under current condition. However, future sea level rise scenarios show emerging high compound major coastal riverine flooding probability along the Southeast Atlantic coast. So under intermediate sea level rise scenario by mid-century, the Southeast Atlantic coast will experience a frequency amplification of up to 5 times. And finally, compared to impact of sea level rise, the impact of river flow change is found to be negligible in most of the locations except the Southeast Atlantic coast. However, even in this region, its impact is considerably less than that of sea level rise. Thank you.
Excellent, thank you. Do we have any questions? We have time for a few questions, if there are any questions.
This is Mary Kay Camarillo. I have a question.
Okay.
So is there any reason, just looking at the cities that you selected for the study, is there any reason that you did not include New Orleans and San Francisco? Is that because both of those have significant river delta systems? Is that part of the reason?
Yes, exactly. Yeah.
Okay.
Because we use the riverine and coastal flood threshold, we just selected the regions and stations that the riverine and coastal flood thresholds are already defined for them. So for the riverine stations in San Francisco and also New Orleans, I couldn't find any stations with defined flood threshold. And because of that, I exclude those from the study.
Does anybody else have any other questions?
Actually, I have another question. This is Mary Kay again. So can you go back a couple of slides? I want to see, I may have misinterpreted.
Now, let me just,
Let's see, the one that shows the final results with the map with the bar graph.
I don't, okay.
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 Too much to ask. Oh, this one, yeah. So
No,
maybe I'm not understanding the results correctly. So the height of the bar represent the risk. That's the risk. So
the risk of failure, yeah.
Okay, so the higher the bar, so you're showing that Washington D.C. has the highest risk of failure.
Yes.
Under all, I mean, I guess that seems surprising to me. Because I would have guessed it would be Houston or Corpus Christi. Can you explain why that result is?
Yeah, because the estuary regions here, so we use the seawater level data and riverine data from the NOAA USGS. So based on the location of the NOAA data, sometimes there's some tidal effect in those data because of the riverine, because of the estuary regions. So in Washington, D.C., yeah, I agree that we may have more risk of flooding in this area on the Gulf Coast. But based on the data provided by NOAA and because of the tidal effect, the compounding effect in Washington, D.C. is much higher. This is based on the compound relation between high seawater levels and river discharges.
Okay, so like the tidal effect would kind of compound the flooding effect.
Exactly, yeah.
Oh, okay.
And for high sea level rise, did you include that as well? Or did I miss that?
Sorry, I didn't get you.
For high sea level rise, because
okay.
You have low and intermediate, but
yes. Because we just do the analysis by the mid-century, the probability of having high and extreme sea level rise is almost not possible.
Yeah.
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 So these are two most probable sea level rise scenarios by mid-century: intermediate, low, and intermediate.
Yeah. Thanks.
Great, excellent. Thank you. That was a great talk.